So let's take a look at this JFET in normal biasing voltage. Notice again the voltage here plus to minus, that's VDD, which is really the voltage here between V drain to source. And notice this voltage is minus to plus, that's here plus to minus, that's V, we're going to call that GS. Now, if we actually take this circuit, we will get maximum current going through ID when what? When VGS is 0. So when VGS is 0, as I mentioned in the previous video, that means I sub D will be maximum. And we call that current actually IDSS. Now, if you try to find what that current looks like, if you graph it, it will look something like this versus VGS. This is VGS here, and this is I sub D right here. And the current actually will look something like this. It's going to start like linear. I'm exaggerating a little bit there. Then it's going to stay flat. Then it's going to go up. I'm going to label a few things on that one. I'm going to call this VP. That's the pinch-off voltage. We'll talk about it shortly. This is VDS, the maximum voltage here. And beyond that is the breakdown, actually when that JFET in a breakdown mode. This section here is known as the active region. And this section, I don't know if I can fit it there, that's the ohmic region. And again, this is, we're going to call this I sub D SS, the maximum ID current. And we get that when you short circuit this one. So basically to get that current here, that's the maximum current, you want to short circuit that when the circuit will look like this. That's when you're going to have it. So you can see this actually, the current is increasing. It looks like a linear straight line. We'll talk about that. That allows me to calculate what the input actually resistance of that JFET there. And once it passes that VP, pinch off voltage, it stays constant the whole time and will go up there. Now the question becomes, why does it stay constant right here? Why is the drain I sub D, the drain current, is constant? Now, when VDS reaches that value, which is VP, the depletion layer, are almost touching. Remember when we looked at the previous video, we said if you look at that JFET, it will look like this. This is the drain, this is the source, you get the P here, P. These two are really connected together. I can jump over this. Internally they are connected together and they come out, and that's your gate, and that's your drain, and that's your source. As VGS start to increase, when it passes this point, these depletion layers, I colored them last time, they become like this. They're touching almost each other. Are touching each other. Now, this means this area becomes really narrow. That channel is called pinch-off voltage. That's the voltage that will make these guys touch each other, these layers. So that's really what that voltage is, that pinch-off voltage. And as you go beyond that, well, you can make that area bigger. So that area will never increase, the size of that between them. So that's why the current does not change. So again, this voltage, VP, the pinch-off voltage, is the voltage that will expand these to make sure that these areas are touching each other. And once you go beyond that, you can't change that. As much as you add them, you're not going to change that. You're not going to make it overlap. So that's what you're looking at. So the minimum value for beyond that's called VP, the pinch-off voltage. And this value is called VDS maximum. What happens when you go beyond that? You are in the breakdown voltage. So this is when the system in breakdown mode. So beyond that, that's the breakdown voltage. So right there between VP and VDS, you can look at this FET or JFET to work like a current source. It looks like it's acting just like a current source. And in case you're wondering what is the IDSS, what does it stand for? It stands for the current drain to source with short gate. So ID current to source, drain to source with a shorted gate. So S for shorted gate. So that's really where the name came from. IDSS, current drain to source. That's the first D. To source. That's where the S comes in. With a shorted gate. That's where the other S came in. And if you look at the schematic, if you ever looked at a schematic of JFET, that number IDSS is given to you on that sheet. On any, actually, look at any JFET data sheet, you will see that value listed there. And also you will see that pinch-off voltage listed on that one too. Now, as we said, to the left of this area is known as the ohmic region. Now, when you operate that JFET in the ohmic region, the JFET becomes like a resistor. Notice it's linear. So in the ohmic region here, we said what? The JFET is equivalent to a resistor. So if it's equivalent to a resistor, then what's the value of that resistor? Well, Ohm's law says R equals what? V over I. That's Ohm's law. So here the resistor we're going to call R between the drain and the source is equal to the voltage, which is actually VP, the slope of that one, divided by that current, which is IDSS. And we call that resistor, RDS, is called the ohmic resistance of a JFET. A lot of terminology here. So let me take actually a circuit and see what will happen. Let's assume, example, I don't mean a circuit. Let's assume here that I was looking at the schematic for a JFET, and I noticed on the data sheet it says VP equals 4 volts and IDSS equals 10 milliamp. On the data sheet, these will be listed. So if I know these are listed, I know when you operate this JFET in the ohmic mode, then we're going to replace that with the equivalent to having a resistor with the value of 4 divided by 10 milliamp, which is equivalent to 400 ohms. And that's actually the value between the drain and the source. So you can look at that as having a resistor here between the drain and the source. Anywhere you operate in the ohmic region, that value stays the same. Now, this is not the only current you're going to see when we look at VGS versus I sub D. You will notice there's, for a different value of VGS, that changes. So let's look at that picture. What does it look like? So normally, if you're looking at JFET on a scope there, this is what you're going to see. This is when VGS equals to 0. And for, let's say the pinch-off value here, I'm just going to use some numbers. That's 4, and this is 10. 10 milliamps, ID in milliamp. Then it might go to 5 at VGS equals -1. This is VGS equals -1. And let's say this might go to 5.5 or 5.6 milliamp. It's not just because this is 1 and doesn't drop by half. We'll show you the equation for in a second there. And this might be when VGS equals 2 or -2. Actually, this should go on this end. Where's my eraser here? It should really cross, comes a little bit faster here. This end, I wasn't paying attention. It should go inside like this. And this one goes like this. This is when VGS equals -2. Then you're going to get when VGS equals -3. And then might go to, these numbers might be 2.5. milliamp. And this might be 0.625 milliamp. And when it goes down to VGS equals -4 down here, the current will look like a 0. And that's why it is 0. Now VDS here might be 4. This particular one, the breakdown is the maximum value is 30 volts. Let's use that one. So the top one, the top layer here again, this is when VGS equals to 0. This is when the gate to source is shorted there. This is when the pinch-off voltage is 4 volts. So the linear, if you look actually in the ohmic region, any one of these, we can treat that during this section here with the resistor of value roughly 400 ohms. We did the calculation for that early. And the voltage will stay the same between, the current will stay the same as long as you're between 4 volts and 30 volts. For VGS equals to 0, that current will be 10 milliamp. If you let VGS equals -1, that current is 5.6 milliamp. If you let VGS be 2, that current is roughly 2.5 milliamp. When VGS equals 3, it's 0.625. When it's negative 4, that's a 0 milliamp. Now, the bottom layer here, the last one, when VGS equals minus 4. The current, the drain current is almost a 0 there. So this voltage here, this VGS, is called the gate source cutoff voltage. So when VGS equals to 4, negative 4, this voltage is called the gate source cutoff voltage. And a lot of times we call that voltage, instead of VGS, we call it VGS off. That's the cutoff voltage. So you see the word off at the end of that. You'll see that number also on the data sheet. When you look at the schematic for that JFET, you will see that number listed, VGS off there. What's interesting about that VGS, actually, if you look at my picture, the cutoff, that's when the current is 0, VGS happens to be negative 4. And the pinch-off voltage happens to be what? 4. Now, it seems like coincidence there, but that's not really the case. VGS is always we're talking about the off value, that's when the current is 0, it's always equal to negative VP, the pinch-off voltage. So this is always the case. This was not by guessing here or just from that picture it looks good. This value, which will give you 0 current, ID current, that voltage VGS will have to be the pinch-off. And again, just look at the data sheet on that transistor, and once you find it there, that will tell you what the maximum value you can put there, VGS to be negative 4 volts or negative VP. Once you reach that, they have I sub D equals to 0. Now, if we try to graph actually what I sub D versus VGS looks like, again, this is VGS. Now, let's look at that picture. Let's try to graph it. So looking at that picture, this is what I see. Let's graph VGS instead of versus I sub D. When VGS from this picture, when VGS is 0, what was the current? 10 milliamps. So if I put 10 milliamp here, that's when VGS is 0. When VGS is negative 1, I get 5.6 milliamp. That's right here. When VGS is negative 2, I get what? 2.5 milliamp. When VGS equals 3, I get 0.625 milliamp. When VGS equals negative 4, I get that number. So if you connect these points, that's what the graph of the current I sub D versus VGS looks like. So this is here 5.62 milliamp. This one here is 2.5 milliamp. And this one here is 0.625 milliamp. Now this picture is actually called the transconductance curve, this picture here. It is the graph, or a JFET graph of VGS versus I sub D. Now, you can see from this, if you try to come up with an equation for that, that's where I'm heading with it. If you try to derive an equation to find the current at any given time, any value of VGS, we know this is not linear. And if it's not linear, so what does that graph looks like? Well, somebody did the math on this, and they found out the equation for that I sub D, it's going to be I sub DSS, the equation that describes that graph there, times 1 minus VGS divided by VGS off, and you're going to square that value. So now by having that equation, we can figure out what the current at any given time. You tell me what value of VGS, and I will tell you what that current, like for example, for this current, VGS off is actually what? -4. So if you want to know what is the current through that, like let's take an example. Can you tell me, here's the question, can you tell me what the current will be, what is I sub D is going to be, when VGS equals, this is the -1 here, the -2 here. So let me show you how I came up with these numbers, the 5.6 milliamps. Some of you were wondering at home, how'd you come up with that number when VGS equals -1? Well, I know VGS off for this one, it's equal to negative VP, which happens to be -4. So if we go to this equation, and I know I sub DSS for this circuit, or this JFET, is equal to 10 milliamp. So you do the math. What is I sub D is going to be? It's going to be 10 milliamp times 1 minus VGS, which is -1, over -4 squared. This is 1 minus, that's a quarter, that's 3/4 here, squared times 10 milliamp. So where's my calculator here? Let's see if that's a 6.2. 10 times parentheses 3 divided by 4, square that, and it's 5.625. And if you try to find it for VGS equals -2, we'll get the other number, the 2.5 milliamps. And if we tried it for that one, if you try it for -4, you're going to have 1 minus 1, which is 0. 0 times anything is 0, and that's why this value in VGS equals VP, the pinch-off voltage, this value is 1, which will make this value 0, and there is no current going through that. So that's the equation I'm going to be using going forward to find the current between the drain and the source. What is that current? I'm going to be using that equation for any example that you give me or we see in the book there. Hopefully that makes sense there. So in the next example, next video, we're going to start solving some problems and show you how we use them. But I had to go through some of the terminology, some of the rules, so you'll understand what's going on with these JFET. I'll see you in the next video.